When you differentiate or you're performing differentiation, you're finding the derivative. So what I'm telling you is today we're going to learn rules for finding the derivative of a power, the derivative of a sum, the derivative of a difference, and the derivative of a constant. We're going to combine them. So as of today, when you find derivatives, unless you're told otherwise, you no longer need to use limits. Okay? We're done with that. I did have some audio on here, and for some reason it's not playing. It was a raucous cheering going on. We can find derivatives without using limits. So as a warm-up, why is the derivative of a constant equal to 0? And this ties actually nicely into our Math 30 lesson this morning, where we had constant polynomial functions. So who can explain to me why the derivative of a constant should be equal to 0, or is equal to 0? I'm saying if f of c is equal to some constant, why is I'm saying if f of x is equal to some constant, why is f prime of x equal to 0? Another way of putting it, and I like this. This is so clean. I don't need to say if something is true, then why is something else true? I can just say, why is d dx of a constant equal to 0? So that's the question. Why is that the case? Who can tell me? Alex?
There's no slope.
There's no slope. If you think of a number, which is a constant, as a function of x, well, what this looks like is a horizontal line at whatever y equals c is. So this is y equals c. So keeping in mind that the derivative is really an expression to determine the slope everywhere, the slope of this function everywhere is equal to 0. It's not dependent on x. It doesn't matter what c is. It could be y equals pi, or y equals negative 3, or y equals 0. The slope everywhere is 0. So, because y equals a constant is a horizontal line, which has a slope of 0, the derivative will be equal to 0. And I can write dy dx, or I can write dc dx. I don't think this is really a difficult concept. It's certainly not some kind of elaborate thing that we need to come up with a complex proof for. It's almost an obvious thing. Unlike the next thing, which is if f of x is x to the n, show that the derivative of f of x is nx to the n minus 1, which is the rule that a couple of you have come up with. What I am telling you is this, that if I had a function of x of, say, x to the 1, I'm telling you the derivative of the function of x is 1 times x to the 0, or 1. If a function of x is x squared, I'm telling you the derivative is 2x to the 1. If it's x cubed, the derivative is 3x to the 2, which, mathematically speaking, the math world gave us a bit of a gift here, because if that's true, and it is, it's a pretty simple rule. It gets a little bit more involved, obviously, than that, but for the time being, that's pretty simple. So again, I want to paraphrase this. This is saying show that d dx of x to the n is nx to the n minus 1. Or, well, I like the second statement best. It's more, what's the word? Succinct. It's more to the point. I don't have to, it's fewer words. So I am going to review the binomial theorem with everybody here. And, well, I'm going to review the binomial theorem with everybody who has completed Math 30-1 and introduce it to everybody who's currently in 30-1. which will be helpful to them later on at the end of the semester when we study the binomial theorem. And it will at least give them an idea of what we're talking about when we show that the derivative of x to the n is nx to the n minus 1. Because I'm going to show it to you, I'm going to prove it to you, we're going to prove it together using the binomial theorem. There are other ways to do it. And there are limitations to this proof, but I think it's the best proof at the high school level. So first of all, and this is nothing you need to write down. There's going to be a video of this so you can watch it later if you want. When you look at x plus y to the 4, we call that a binomial power, or an exponent on a power. Man, I'm having a tough time today with words. We call that a power of a binomial. It's x plus y raised to the 4. And if I asked you to simplify that, then without the binomial theorem, you have to multiply x plus y by x plus y by x plus y by x plus y. I think I said it 4 times. And what you would probably do is you'd take the first pair of x plus y's and FOIL them out to get x squared plus 2x plus y squared plus 2xy plus y squared. You would do the same thing to the second pair, and then you would have to multiply out that trinomial by the trinomial. And you would have to take that first x squared and multiply it by the x squared in the second trinomial. You'd take that first x squared times the 2xy in the second. So what I'm doing is I'm multiplying this x squared in to all of these. And then I would say I'm done with that x squared, and I would move on to the 2xy. So now I'm taking the 2xy in the first by the 3 things. And it doesn't matter. I mean, you can go through and you can double check. You know how to do this. You're going to get those 3 terms. And then you would be moving on to the y squared in the first set of brackets. And when you multiply it through, you get x squared y squared. You get 2xy cubed. And you end up with y to the 4. And you would add these things together. You have x to the 4. You have a total of 4x cubed y. You have a total of 6x squared y squared. Then 4xy cubed, and then y to the 4. You guys are all with me, I hope. I didn't go through slow enough for you to do it on your own, but you understand what's happening. Well, the thing I want to point out, and everybody who's completed 30-1 should know this, is there's a pattern here. Forgetting about the coefficients. The pattern is that this binomial was raised to the 4, and the first term has the x raised to the 4, and it doesn't have any y's. And the second term has x raised to the 3, but it has a y. And then it's x to the 2 and y to the 2. So what's happening is the sum of the exponents of the variables in every term is always 4, always, because it's raised to the 4. But what's happening is all of those exponents are carried by the x in the first term, and none are carried by the y. And then there's a handoff, one number at a time. Each time you go to a new term, you lose an exponent on x and gain an exponent on y. The numbers can be found in a way that you're not familiar with, okay? But that is what x plus y to the 4 is. Well, it turns out that x plus y to the 4 can be expanded, and I will explain what this other notation means in a second. The first term is going to contain x to the 4, y to the 0. The second will contain x cubed, y to the 1. Don't worry about the other stuff just yet if you are in Math 30-1 right now. And again, there's that handoff, one exponent at a time, until we've run out of numbers on x to give y. Now what this is, this is called 4 choose 0. And what it means is if I have 4 individuals, Alex and everybody in this row, 4 choose 0 is the number of ways I can pick none of them. And I've just done it. There's only one way I can do it. I just ignore them. So 4 choose 0 is 1. 4 choose 1, and I'll make this a little more practical here. I have those 4 individuals, and I have one gift card that I've decided I don't want, and I'm going to give it to somebody. 4 choose 1 is the number of ways I can choose one person of the 4 to give it to. So I can choose this person, this person, this person, or this person. And that's going to be equal to 4. 4 choose 2. Well, I have 2 gift cards. So what can I do here? Let's count them off. 4 choose 2 would be 1, 2, 3, 4, 5, 6. It turns out it's 6. There's 6 ways to do it. And it's pretty interesting that there's a connection between these combinations and binomials. 4 choose 3 is 4, and 4 choose 1 is 1. So it turns out that that is the same. That is the same as this thing at the bottom of the screen. So I hope that if you've taken Math 30-1, you remember all that. I'm not going to show you the general term because then that might be confusing to those who haven't. And I hope if you haven't completed 30-1, you followed the gist of my argument here. But one thing I want to point out to you before we go on with the proof, which is really the kind of the bulk of what we're learning today, is that this number is this number. In every term, the number you're choosing from is the exponent on the binomial. And what else is important is the first term starts off with this being 0, and then it goes to 1, 2, 3, all the way up to 4. But more importantly, the exponent on y always matches the number you're choosing out of the total. That's the pattern. Okay. Now, we're going to use that to prove this statement. Because if f of x is x to the n, and we apply dy dx equals the limit as h approaches 0 of f of x plus h minus f of x over h, f of x plus h is going to be x plus h raised to an exponent. It's going to be a binomial raised to an exponent. And I will warn you right now that the top of our limit expression is going to get very long. So long that I don't have enough room to put it here. So what I'm going to end up doing is I'm going to have the limit, and I'll have stuff eventually, all kinds of stuff, and it will continue, and then it will be over h, okay? So if you want your work to be nice and tidy, you'll want to either write small, or if you don't, or arrange it so that it's very clear to follow. What is this going to become? Whoops, I didn't mean to do that. It's going to become the following. This will be, I'm just going to stop writing dy dx equals. I'm just going to write the limit as h approaches 0 of f of x plus h is x plus h to the n minus f of x is x to the n all over h. So this is your first foray, I think, into an actual proof of any kind. See, it would be very easy for me if n were 2 to use this formula and show you that I get 2x for a derivative. And I could do it if n was 3 and show you the derivative is 3x squared. But the idea of a proof is to prove it for any value of n. All right? So I'm going to expand x plus h to the n. And I know that seems a little weird because I'm expanding something and I don't know the exponent, but it doesn't matter. My first term in the binomial expansion will be n choose 0, x to the n, and it will be h to the 0. I feel as though I shouldn't need to write the h to the 0 in there, but I'm going to. That's the first term. And what's going to happen, and I can go back and show this to you, is this number I've highlighted in green starts at 0 and it goes up by 1 each time until eventually you hit the end. So this number that is currently 0 here in this term is going to go from 0 to 1 to 2 to 3 to 4 to 5 to 6, all the way up to n. The difficulty is we don't know what n is. So what we're going to have in the middle of this expression is 3 dots saying we don't know how many terms there are. My next term in the expansion of x plus h to the n will be n choose 1. It will contain x to 1 less, and it will contain h to the 1. My next term is going to be n choose 2. It's going to now contain x to the n minus 2. Remember, the exponent on the x always falls off by 1 each time, and the exponent on the h goes up by 1. Now, I feel that's enough to make my point. I could put a few more terms, but let's just stop for a second here. There's going to be some point where this number on h is going to get closer to n. Right? Just stop for a second and think about this, that if n were 5, the very last term would contain h to the 5. Right? And the term before that would contain h to the 4. And the term before that would contain h to the 3. But what that means, and you might want to hold off on writing anything until you see how I lay this out, is my very last term in this expansion has to contain an h to the n. It has to. Right? And my x has to contain nothing. And my choosing has to be n choose n. In other words, this last term will be where we run out of handoffs of the exponent. The term immediately before that, so I'm writing backwards here, would contain 1 less than n. Because don't forget, h is going up by 1 each time, so if it hits n, then it must have just been at 1 less than n. And this exponent on h matches, I don't want you to mess up your work here, but this exponent on h matches the number we're choosing out of n. So we are going to have n choose n minus 1, and the x ends up being 0 here, which means it must have been 1 here. And since I've gone up to the number 2 here, I guess I could go up to the number 2 here. I'm just moving things to give myself a bit more room. That this would be n choose n minus 2, x to the 2, h to the n minus 2. And again, this is dot, 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 plus. There's how many terms are in between these 3 and these 3? I don't know. Depends what n is. If n is 1,000,000, then there are 999,994 terms in there. 5, because there's one more term than n. But I don't want to get into that. Okay, that's something different. And this is over h, except that it's very easy to forget we have to subtract f of x. And this is a proof that if you wanted to do this proof officially, I mean, I've written it out, but I think the proof requires words as well. And you're going to have to get used to this, that sometimes proofs in calculus are logical just as much as they are algebraic. There's a brilliant proof we'll do in the Unit 4 about the area under a function and how it relates to something called the antiderivative. The algebra is this much work, but the rest of it is all reasoning and diagrams. So don't forget, this is the limit as h approaches 0 of this whole thing. But what is n choose 0? It's 1. It doesn't matter whether I'm choosing nothing out of 5 or nothing out of 17. There's one way to do it. And what is h to the 0? 1. My point is, this is x to the n, which is a relief because we can't have any terms left unless they all contain h. So now what we have after we cancel these, and we're almost done the proof, is that. But there's a common factor of h here. Every term has an h. So if I factor that h out, and I'm going to freeze this on the other screen so I don't crowd my work. You have it in front of you. I now have the limit as h approaches 0, and the x to the n minus x to the n is gone. I'm going to factor an h out of that entire mess of the top of that argument. And what will I have left? This term here will contain an n choose 1 and an x to the n minus 1. How many of you see the solution to this proof right away? Okay. Those of you that don't will see it in a minute. My next term, which is what I get when I factor h out of this, will be n choose 2 x to the n minus 2 h. I'm not going to do the same kind of thing. I'm not going to actually factor it out of this as well from the end. I'm going to do one more. And I'm factoring out the h out of, I guess I don't have that one. I won't bother then. I have a whole bunch of terms left, right? How many? It depends on what n is. But the point is, plus all terms containing a factor of h. I mean, this term has a factor of h. The next one will have a factor of h squared. The next one will have a factor of h cubed. It doesn't matter. And the last one will have a factor of h to the n minus 1 because I'm factoring an h out for the last term. And this is over h. Well, that's pretty good. Because now I can cancel the h's, and now I'm going to substitute h equals 0 in. And of course, what's going to happen is this term and every other term after it are going to become 0. Because h is equal to 0 in the calculation of the limit. I mean, I could rewrite it and put a 0 here and indicate that algebraically, but I think that's enough. When we put 0 in, what you are left with, and don't forget, this was the derivative with respect to x of x to the n. What are we left with? N choose 1, x to the n minus 1, which is pretty slick. N choose 1 is n. 10 people and I want to choose one of them. How many ways can I accomplish that? 10. So, done. We've proved it. Well, I guess one more thing. We should write it as d dx of x to the n is n x to the n minus 1. So now you know how to find the derivative of x to the n. You do not have to use limits. You just say, oh, x to the 11, the derivative is 11x to the 10. Any questions about what we did there? All right, I'm going to go through some other rules here. So this is the one we've already talked about. the derivative of a constant says, and again, I want to talk about this interpretation or this way to describe the rule. If a function is equal to a constant, then the derivative of the function is equal to 0. However, I think this is more, I don't know, succinct, elegant, to the point. I don't know how you want to describe it. d dx of a constant is 0. It's a much cleaner way of just saying what's on your mind. The derivative of x to the n, same thing. If f of x is x to the n, then f prime of x is n x to the n minus 1. We're taking the exponent, we're wrapping it out in front, and we're dropping 1 from the exponent. Don't confuse that with logarithms, which if you've taken logarithms, there's something similar to that. The derivative of a constant multiplied by a function. It turns out the derivative of a constant multiplied by a function is the constant times the derivative of the function. And I can very easily tell you the proof to that. Imagine that this question said, show that the derivative with respect to x of some number times x to the n is that number times n times x to the n minus 1. I could have very easily said that. And the only thing that would have changed is we would have had an a in front of both of these. We would have had an a here and an a here. And we could factor that a out and just have it tag along in our limit work and then throw it back in at the end. So the derivative of a constant multiplied by a function is the same thing as the constant times the derivative of a function. In fact, when you take a look at the next rule, it says the derivative of ax to the n is an x to the n minus 1. That's just this rule and the one we just proved put together. Right? If the derivative, everybody, let's see if this makes sense to you. If the derivative of this function is that, and I'm telling you the derivative of a constant times a function is the constant times the derivative of the function, constant times the function is the constant times the derivative of the function. You catch my drift here? In fact, I would say to you that Rule 2 is rarely used. You're always just saying take the coefficient times the exponent and drop 1 from the exponent. And if the coefficient is 1, then I guess it's Rule 2. And Rule 3 is never really used directly until we get to some other proofs later. And this is unique. We could prove it. We could use the same approach that we did with x to the n. The derivative of a sum is the sum of the derivatives. That is not always true in math. It's not. Is the square root of a sum the same as the sum of the square roots? No. Is the square root of a product equal to the product of the square roots? Yes. But this kind of rule, it's almost a distributive law, is not true for everything, but it is true for functions and derivatives. So I'm telling you the derivative with respect to x of 4x to the 10 minus 2x to the 3 is the same as the derivative with respect to x of 4x to the 10 minus the derivative with respect to x of 2x cubed. Are you with me on that? Okay. And the constant multiple rule says that the derivative with respect to x of 4x to the 10 is 4 times the derivative with respect to x of x to the 10. Getting my drift here? I don't think you'd ever need to do that. You would just say the derivative of 4x to the 10, and I hope you're with me, is 40x to the 9. But all of these rules are consistent. we could say minus 2 times the derivative with respect to x of x cubed. And then you could apply this d dx to x cubed to get 3x squared. You could apply the d dx to x to the 10 to get x to the 9 times 10. All right, let's practice some of this now. Imagine, wow, if I said what is the slope of the tangent to this function, you should know it's 2 because this is a straight line with a slope of 2. But if you apply the rules, and I'm going to be excruciatingly detailed on this. You don't have to write all of this down. This is what we are asked to do, right? But that means the derivative with respect to x of 2x plus the derivative with respect to x of 3. And I'm not going to do this every time. This is a real pain. But the derivative of a constant times a function, 2 is a constant, x is a function of x, is the constant times the derivative with respect to x of the function, and this is d dx of 3. So, what is the derivative with respect to x of x? We take that exponent on x and wrap it down in front and get 1x to the 0. If you want to be clinical about it, you get 1x to the 0. What is the derivative of 3? Well, the derivative of a constant is 0. So this is 2. Which, you don't need to do any of that work. You could just say the derivative of 2x is 2, and the derivative of 3 is nothing. I'm not going to do that over here. Just take a minute and take a look at that. Did I write something down incorrectly up there?
No. The answer was 2, right?
The answer is 2. I'm sorry, I should have paused there a bit. Yes, the answer is 2. Which meshes with our idea that 2x plus 3 equals y is a straight line with a slope of 2. Is everybody okay with how we get 15x to the 4 minus 6x squared? Done, boom. Imagine putting the x plus h thing in here and you'd be there for 25 minutes. For root x, well, all we have to do is put this function into a form that we can apply a rule to. And root x is x to the half. So we swing that half in front. The old coefficient times the exponent. Base raised to 1 less than the exponent was, and you end up with 2 x to the negative half, which we would most likely write as 2 over root x. Because 2x to the negative half is this. And you can write root x instead of x to the half. Same kind of idea here. Before we differentiate, what we need to do, well, you don't need to. You could think around this. But it helps to write things explicitly as a number times x raised to a number. And let's face it, that's what this lesson is about. By the way, I should throw this out because I want to be clear here for those of you taking calculus next year. We use the binomial theorem to prove that main rule, but the binomial theorem is all about n being a whole number. So we haven't proved that it works with fractions or decimals, but it does, okay? The proof for any value for the exponent is complicated. I'm just rolling it around in my head here, and I don't even know where I would begin in high school, okay? I don't know where I would begin, period. So we differentiate this. I hope what I'm about to write makes perfect sense. I multiply the old coefficient, the original coefficient, by the exponent. So I get negative 4. I rewrite the base. I drop 1 from the exponent. And then I do the same thing to the other one. Given that the first original expression was fractions that were not put together, we're okay to leave our answer that way as well. If you look up here, don't write this. Well, you could write it if you want. I don't care. That is just not true. You cannot apply that exponent or power rule unless you're wrapping the exponent around x. This is not the derivative. You can't just swing that 2 around, rewrite the whole base, and drop 1 from the exponent. We have to expand this out first. And now would be as good a time as any to tell you, we are going to finish the lesson today, and then for the rest of today and tomorrow, it's a practice day with derivatives and problems, okay? Please remind me a little later to give you that assignment. One of you. So we FOIL this out and get 4x to the 4. We get minus 4x cubed. It's just we happen to get minus 4x cubed because the outer and inner are both negative 2x cubed. And then we get plus x squared, and now we can differentiate it. (16x cubed minus 12x squared plus 2x), which is not equal to this. It's not. I mean, look at it. If you multiply that 2 through, you're not going to get that thing. There's a rule called the chain rule that we need to know before we can differentiate something like this without expanding it out. And the reason why we're going to need the chain rule is if I said, what is the derivative of this? Nobody wants to take 2x squared minus x times itself 12 times. But maybe there's some weirdo out there who does. No offense if it's one of you. But any questions with E? Right. So now we get to a couple of problems. What's the equation of the tangent to this function at this point? When you did these problems before, do you agree that 3/4 of the time was spent finding the slope of the tangent? That's just a rough estimate. Well, dy dx, or f prime of x, is equal to 3x squared. What is it you need to know to find the equation of a tangent line? The slope and a point. Well, the point is 2 comma f of 2. And finding f of 2 is pretty trivial. Can you find f of 2 for me and confirm that you get 7? Put 2 in for x, you get 7. So the point is this. What is the slope? Well, the slope is equal to f prime of 2. F prime of x is a formula to calculate slope. So if you put 2 in, you get the slope. That's child's play. And now what you're dealing with, everybody, is a grade 10 question. If the slope is 12, it is 12, isn't it? Yeah. If the slope is 12 and it passes through that point, what's the equation of the line? I feel as though we could just end it there, but we'll finish it. We're going to use y minus y1 equals the slope times x minus x1. Y minus 7 equals 12, x minus 2. You know, do with that what you will. If you want to rearrange it for y, if you want to go ax plus by plus c equals 0, you're going to get some variation of 12x minus y minus 17 equals 0. But I would like you to do the work on paper and confirm that that is correct. I'll have negative 24, but I have to add the 7. All right, let's just take a look at something. By the way, this is y equals 12x minus 17 if you want to go slope-intercept form. Just show this to you quickly. And by the way, this is what I've meant earlier a couple times where I said it's going to become easier to find slopes of tangents, but the problems become more complicated or complex. So this is the graph of y equals x cubed plus 1 or minus 1. This is the point of tangency. And this, I don't know if you can see it, 12x minus 17 is tangent at that point. Any questions with that example? At which points on the hyperbola xy equals 6 is the tangent line parallel to 3x plus y equals 7? So let me explain to you what this is asking. Where are we? There we go. xy equals 6. If you rearrange that for y, you get y equals 6 over x. And that's what it looks like. This shape is called a hyperbola. Okay, it's not a big deal. We don't learn about that in Math 30. But there are going to be points on this curve where the tangent line will be parallel to this line. So what is this line? This line is y equals negative 3x, which has a slope of negative 3. Okay. If the tangent line is parallel to y equals negative 3x, the tangent line has a slope of negative 3. Would you agree? And you know what? I'm going to actually put it in. I don't think I have it in here. I'm going to enter a function y equals negative 3x. Right? Would you agree that I can draw that line with that slope tangent to this curve? It would be at these 2 points. I think you can kind of see visually there will be a point on each arm of the hyperbola. We are asked to find the coordinates of those points. So, this is not a difficult question. The function that the lines are tangent to is 6 over x. And the tangent lines are parallel to y equals negative 3x, right? So the tangent lines, tan lines, on a beach. The tan lines have a slope of negative 3. Let's just walk away from that for a second. The slope of the tangent lines are negative 3, each of them. What is the derivative of the function? We're done with this. Y equals 6 over x is the same as y equals 6x to the negative 1. So finding the derivative is easy. It's y equals, dy dx rather, equals negative 6 x to the negative 2, or dy dx equals negative 6 over x squared. So we have 2 statements here. The derivative of the function is this, and the slope of the tangent must be equal to this. But the derivative is a way to calculate the slope of the tangent. You put in a number for x, and negative 6 over x squared gives you the slope. So it isn't that I'm saying, what's the slope at x equals 5? I'm saying, where is the slope negative 3? And that means we have to find out where this happens. We solve that. Multiply both sides by x squared, cancel the negatives, divide both sides by 3, take plus or minus the square root, and I love that math doesn't lie. There are 2 values of x where the tangent line will have a slope of negative 3. So, I just want to write the equation of the original function here. What are the coordinates of the 2 points? Root 2, comma, 6 over root 2. Negative root 2, comma, 6 over negative root 2. And I hope you're fine with me when I say over negative root 2, just saying negative 6 over positive root 2. So let me draw in the tangent lines now. Let's get rid of this. Don't worry about the equations. We weren't asked to go that far. We could. But I want to open up my points of tangency here and show you the coordinates. Square root 2 for x, 6 over square root 2 for y. Negative square root 2, that's the computing language you use, SQRT brackets. Negative square root 2, I don't know if you can see it. Can you? You guys have good eyes. And then negative 6 over square root 2. It all meshes. It all looks right. The numbers match. Clearly, these are tangent lines. Any questions with that final example? The 2f of x is there for the tangent lines. I just put it into point slope form and I calculated what it would be to enter for y. Okay, so in a way, kind of a lot to take in today, but it's a huge relief. I mean, it really is. Just want to open something up. Give me 1 second. It's a huge relief, particularly this, right? I mean, this is kind of a marriage between these 2 rules, but it's what we use all the time. And if you use this rule that I've highlighted, the other 2 rules will happen on their own, okay? We use this without even knowing we're using it. When you find the derivative with respect to x of 4x squared plus 2x minus 1, and you write 8x plus 2, you're using this rule. You're saying I can just differentiate each piece and add them together. So what you're starting to work on today are the problems on page, Alex?
88.
Page 88. And then you're going to continue working with them tomorrow. We need a day to just practice differentiating before we get to something called the product rule, and then the quotient rule and the chain rule. But we're getting there, okay?